Thank you. So I changed the title because first I intended to speak about dilaton hair, also hair. So the one word was preserved, it is, but now inspired by yesterday discussion about BMS or like charges, I switched to this subject. So let me start. Page down, or what is this one? Ah, okay, it works. I took this from my lectures, which I gave at Vitoria. So I think you understand this picture, well understand this picture. So Weinberg considered emission of a soft photon or graviton here from the external leg of any 4-point diagram. And this consists of 5 diagrams. Here is from the core, and those are from different legs. So in the infrared limit of is emitted graviton or photon. So first it will be graviton. There is a infrared divergence because of that region, and but the last diagram remains finite. So finally we have something like that. Now the soft factorization used by Weinberg, it's just the first time of that, and that I took from Kachas and Sreminger. Now people understood that one can further expand. This is the amplitude with emission of n particles. There were 4 of them. And Kn plus 1 is the graviton, and epsilon is inserted just to mu is a graviton polarization tensor. Higher order term will not be used here, but now people know how to obtain them also from BMS considerations. So with this factorization, the whole amplitude will be just the sum of 4 legs and a core amplitude, and the external leg, each of them will have 0 in denominator. So finally, what Weinberg did, it was the low energy theorem in the spirit of Gell-Mann and Law, taking the contracting with full momentum of graviton, which should be 0 by transversality, which is just the word and identity. And this gives you the term which is non-singular, which is 0 in the infrared limit, because the contact, the core diagram do not diverge, does not diverge, but the rest are diverging, so there is cancellation of those scalar product after you multiply by k. And you obtain just a finite quantity here. So the factorized amplitude does not enter. You have just the sum of kappa A. Kappa A is the coupling constant of each leg with graviton. So they are assumed to be different at the beginning, and finally you get this the sum kappa A P M P mu A is 0. And this should be taken together with the conservation of for momentum. So resolving this system, Weinberg finds that all kappas should be equal. And this is the proof of universality of gravitational interaction. So the low energy argument for gravity gives just the universality, while for other spins, if you repeat this for spin 3 with a tensor field of the third rank symmetric tensor, you will get, instead of the previous identity with 1p, the identity with 2p's. And together with conservation of momentum, they just give you that all coupling constants are 0. So in the classical limit, thus in the classical limit, the spin 3 doesn't interact with gravitons. And finally, recall that for in electrodynamics, it just gives you conservation of charge. So this is one thing which was just used in the recent discussion. And another is gravitational memory, which is different, it's purely classical. And it is, but the result is related to Weinberg theorem as follows. So I took this from the paper of Garfinkel, which is very concisely written. So consider two particles which are in a free-falling gravitational field generated by some distant sources of waves. And delta xj is a relative displacement of those particles in the field of gravitational wave, which described by the Riemann tensor, yes? So d is the distance, initial distance between the particle, and this is geodesic deviation equation. Now, the R, the curvature tensor, is generated by some source, and in non-relativistic limit, it will be just a quadruple formula. So this is a quadruple formula, and P is some symbolic, it is a symbol for projection operator, because you need, of course, here to do it more carefully with angles and directions and so on. So this is just symbolic, but it does not change the final dependence and final effect. So Q is quadruple moment of matter, the source of radiation. And if it is, the source is also the system of point particles, it will be that. And finally, combining all those formulas, we get this expression, which actually was derived by Zeldovich and Polnarev in '74. So after passing the wave, these are, we suppose that particles producing gravitational wave are just colliding, and they have some, they stabilize at infinity, at minus infinity, and this is the change of these quantities, which gives you displacement which doesn't depend on t, on time. So it is just the memory of passing gravitational wave. And just you see that the quantity is the same as Weinberg obtained in those quantum considerations, so it is somehow classical counterpart. Now, in full nonlinear treatment, it was done by Christodoulou. The same for electromagnetism. You can show that there is a memory, but there is a velocity memory. Now, you calculate in a similar way. You calculate this difference of velocity of two charges. In the field of electromagnetic wave, which is also created by other charges and so on and so on. So you calculate in a similar way, and finally you obtain this quantity, the memory, velocity memory for about about electromagnetic waves, which passed. Now, how people use the BMS considerations to derive this result? So let me just recall you that BMS is the following. There is a Penrose diagram for Minkowski, and this is Cry plus, Cry minus, and the cones, which are two-dimensional spheres, each point is two-dimensional sphere, and you parameterize the sphere by complex coordinates. It's stereographic projection. So, and you choose the retarded time. So future null and flimsy in Minkowski space has such metric, has such metric. And any asymptotically flat space-time with matter, which is a solution of Einstein equations, will have this kind of asymptotic. But of course, there will be other terms, higher terms, which contain 1 over r distance in denominator, and the rest depends on z bar. Now, what is called supertranslations, it is just a conformal transformation of the sphere, which are accompanied by some transformation on U, operator acting on U. And F here is an arbitrary function of two holomorphic, anti-holomorphic variables. So this acts on Scry plus, which is the future narrow infinity, and similar transformations acts as Scry minus with V, which is T plus R, which with V here plus here and the same here. So there are different sets. This is algebra. They form the BMS group, and there are two of them, minus and plus infinity. So the achievement of Strominger was that he showed that if we if we take just the direct product of those BMS plus, BMS minus, which are transformations on Scry plus and Scry minus, and impose some identification of those points, which selects a subgroup of that, and this subgroup will be the symmetry of S matrix. Then from this symmetry, a word identity can be derived, and this word identity from this, it can be soft photon factorization theorem. Factorization theorem of Weinberg can be just derived. So the final step was a recent paper by Hawking, Perry, and Strominger, and I just show here the title. And it is not the abstract, but it is the end, because in the abstract they were more optimistic than at the end, saying that of course it is okay, but it is doubtful that it's a real solution of information paradox, which is more classical than this quantum here. So this is just for introduction and to just explain my interest to the problem which I consider further. So the problem is just now come back to the Weinberg argument. And suppose that this particle, which is emitted from the core, is itself massless, yes? So it is just the massless charge which interacts with massless photon here. And then we will have additional singularity, which is called collinear singularity. And such singularities are well known in QCD because it is typical situation for gluons. And people know how to fight with collinear singularities. It is just not like infrared for collinear. To eliminate collinear singularities, one recipe which was suggested by Lee now in Berkeley, the so-called famous Lee-Nauenberg theorem. The prescription is that you have to prepare initial state with soft gravitons. Just some reminiscent of this BMS proposal, you have to prepare initial state of gravitons, of soft gravitons independent of this whole scattering. And then you cancel that. So finally, this is not a problem, but it should be mentioned. So which are realistic situation? First, the big question, why God did not create massless charges just interacting with photons. Maybe the reason was that the theory would be inconsistent. But people studied this question. There were many very beautiful papers on that. Finally, the result was that there are problems. There are problems, but they are not so radical. So finally, doing calculations carefully, you can obtain reasonable results. So maybe the reason for God was another, and we don't know. But of course, there are realistic situations where massless particles interact with another massless particle. So I just distinguish the source as particle. And now I will be interested by radiation. So the source particle is called massless object called particle, and the radiated field called field. So we have in general relativity, of course, neutrino. Let's suppose that it is massless. Now we have gluons. Now we have the problem of massless charge in QED. And this is, there are arguments against that, but still not, it is not a radical objection. There is a problem of collinear divergences, but collinear divergence is solved. It is now recognized that it is not a problem. Now, several people, including Gribov, Wax, some other, showed that there is a screening, and if you consider QED with massless electrons, you will have an effect similar to confinement of a charge. So there will be charge screening. But the distance at which the charge of massless particle is screened is very big. It is exponential of inverse alpha in fine structure constant. So this charge screening exists, but it doesn't prevent you to find situations where charge, massless charge is created in a shorter distances, and so it should be somehow observed. Another argument is that the renormalization group gives you infrared stable point, which is 0 for the charge, depending on mass. It is 0, and it can be interpreted that in the classical limit, the effective charge going to 0. But it is also the case where you deal with purely, so the situation changes substantially if you consider external field. So the charge will not be free, but just bounded. And of course, we can consider classical motion of massless charge in external field. I will show how the equation looks. Now, recently there was some interest into massless QED in external magnetic field, and very reasonable results were obtained. One idea, which is worth to be mentioned, is that if massless charges exist, they do not radiate. Why do not radiate? This will be just my problem, which I will consider in detail. But the argument of this kind can be encountered in the literature. So what about radiation from massless particle in general relativity? This was never considered as far as I'm aware. And I will show that it leads to catastrophe. Now I'll come back to massless QED. So whether this theory is not contradictory, I just mentioned some names, these papers of 60s, starting from 60s to 90s, and very interesting papers. So the massless QED is a special theory, let's formulate that way, but still not much contradictory. Now, can classical electrodynamics describe radiation from massless charges? This was discussed a lot recent 5 years, and most people propose that it should, but it gives zero. So classically, massless charged, according to their arguments, massless charge should not radiate, but this is wrong. Now, another related question, if we consider ultra-relativistic limit, it should be somehow related to massless limit, but are they the same? But no, people who worked with synchrotron radiation knows well that these limits are not the same at all. So to continuously pass to massless limit in some formula, it's not sufficient to take gamma Lorentz factor equal to infinity. Now, and finally, we assume that nature is quantum, so first we should consider this problem of radiation from massless particle in quantum field theory, but then whether one can expect that it will have classical limit. And this, the answer is no, it is just the explanation of some apparent inconsistencies. So this is the references. So let's start with Larmor formula of classical electrodynamics in the massless limit, and considered in the massless limit. So this is the power of radiation. So it is not the total radiation, but it is just the radiation per unit energy per unit time of the charge in magnetic field H of mass m and energy E. So the energy in the massless limit is finite, or everything is finite. We have m pure divergence m to the power 4 in denominator. So, and this is somewhat strange. And my interest was just how can I answer the students' questions? So if the mass of radiating particle is very small, not the energy big, but the mass is very small. Suppose that neutrino, which has a small, very small mass, and suppose this formula is okay, but now consider the limit of zero mass, it diverges. But diverge is something not good. So whether this formula is applicable to true massless charge? So the obvious answer is that it is not. Another problem is linear, the retarded potential. The retarded potential, actually, let's first just take, there was a discussion how correctly to define solution of D'Alembert equations. D'Alembert equation with the source which moves with the velocity of light. Because the retardation is a subtle thing, so you have, and the idea was that the solution should be defined as distribution, as generalized function. In that sense, that it should be integrable with some class of test functions and so on. But this formula does not make the correct answer in this sense because it diverges on a line. So if you remember the linear Wiechert potential, this should be the ratio of velocity over the speed of light, 1 minus v over c cosine theta. But now v is equal to c, so it is just the pure divergence. When you see cosine theta is the angle of observation, the angle at which you look at the system with respect to the velocity. So you just have a linear divergence in the direction of the velocity. Of course, we understand that it is very similar to collinear singularities in QFT, which I showed on the diagram with external legs. Because on those diagrams, let's see it again. We get here, if this particle is massless, we will get here just the scalar product P over K, and it will be proportional to 1 minus cosine theta, where the theta is the angle, the same kind of So Lechner and co-authors wrote 4 or 5 papers on that, discussing how correctly make subtractions for treat this divergences, how to define this as distribution, and finally the net result was that there is no radiation. So all subtraction just subtract radiation too. But the argument is that this is the whole. This is the total power, and this is the total field of a massless particle. So these quantities are divergent, and this shows that there is a problem. But they don't explain the origin of this problem. So the origin is that the spectral decomposition of radiation is correct. Let me first explain you how massless charge moves in external electromagnetic field. So we have to restart because if there is no charge, you have introduced a Lagrange multiplier here, E, and this is the charge, and lambda is some undetermined parameter on the word line. And if we choose lambda equal to t, which is x0, then variation of this action will give you this equation for the Lagrange multiplier. The right-hand side is just the product of v velocity by electric field, and it shows that it can be should be identified. This multiplier is not defined. It remains. It's a physical question how to define it, and this equation shows that it should be identified with the energy, kinetic energy, E. Now the equation becomes quite similar to well-known equation for massive charge, and the remaining special part of the equations, instead of mass, there will be just the energy. So this perfectly fits with massless charge. You can rewrite this special part of equation using the 3 momentum, introducing it that way. So like for massive particle, and the equation will be of the usual form. So description of using momentum is just does not. It's continuously related to massive case. Now we have v square, which is 1, and differentiating we get that the velocity and the acceleration are always orthogonal. So the particle, massless particle, cannot be accelerated along the velocity. This is clear because the velocity is constant, but it can be accelerated in transverse direction. And finally, we can, from those equations, we can express acceleration in terms of the energy and the force and velocity. So it is double. So such a charge can rotate in magnetic field, and it is just transversal acceleration there, and it is typical case. So actually, radiation from a charge rotating in magnetic field is a general case because acceleration should always be orthogonal to the velocity, and this is just the case. Now, the frequency of rotation will be like the same. So repeating all calculations, we get the Schott formula, which is a formula for spectral distribution, spectral angular distribution of power in terms of composition or discrete harmonics. So discrete harmonics of the rotation velocity. And this is Bessel function, well-known formula, which was obtained more than 100 years ago by Schott. And it remains valid if beta is V over C when it is 1. The only problem is that you should use different, other approximations that usually used in the theory of synchrotron radiation for Bessel function of large index and large argument. We understand that in ultra-relativistic case of massive charge, radiation is concentrated on high harmonics of rotation. Nu is just the harmonic number of the harmonic, and these nu are the sum here contain the factor nu square, which is increasing, but Bessel functions will be somewhere in the region of the argument close to index, but smaller than index. And there are different approximations, mostly by McDonald functions. But those approximations fail because if beta equal to 0, something diverges there. And usual derivation shows that the sum is cut at the number of harmonic, critical number nu, which is of the order of energy over m to the power 3. And clearly, when mass going to 0, there will be no cutoff. This is using those approximations, but you should use other approximations. I did not show which. There are similar in terms of k, but different. And you confirm this result. So this formula, it is discrete, but of course, for higher nu, you can replace it by continuous distribution over mu, over nu. And you find that there is no cutoff. And this is the reason why the previous Larmor formula, which is the sum over all harmonics, it diverges. While classical theory still allows you to perform consistent calculation of spectral distribution, and this spectral distribution is simply given by the same Schott formula with velocity equal to 1. And what you can show that using using some asymptotic formula, of course we understand that in all cases nu should be big in the validity of quasi-classical approximation, and because the charge is not only ultra-relativistic, it is just moving with the extremal velocity. So just passing to continuous distribution over omega, you get this result. And we see that this is equivalent to increasing function as a power of omega 1 over 3. It diverges, and it is similar to it is a kind of ultraviolet catastrophe, but now in radiation, but not in the black body radiation, as Pauli discussed it. But how to fight with this problem? Of course, we have to pass to quantum calculation, because in quantum theory we did not foresee any problem with radiation of a charge which moves in the external field. We just have to use the formalism of classical external field, and this was. But first, we can try to improve our classical calculation by just introducing quantum cutoff at the maximal frequency, which is equal to energy particle divided by the Planck constant. And this gives you, so integrate the formula which was obtained classically, integrate you this formula up to quantum cutoff. Then we obtain this formula. And what we see here, that the dependence of on the Planck constant is not analytic. It is h to the power 2/3. And the charge is also to the power 2/3. This means that the effect is not perturbative in the sense of quantum electrodynamics, if this formula makes sense indeed. And we will see that it makes sense. Only coefficient will be different, but it is non-perturbative with respect to magnetic field, with respect to E, the charge. And it has no classical limit. So in the classical limit, the result is diverging, and this is compatible. It is just what we expected using the Larmor formula. How to calculate in quantum theory? So the direct way is just to take solutions of Klein-Gordon or Dirac equation, depending on spin, in external magnetic field. And the well-known results show that it is quantized in terms of Landau number n, and the velocity in the direction of magnetic field. So radiation corresponds to transition from one n to another. And we have to sum up over all n prime, starting with some initial energy and initial velocity along magnetic field, and get the total power. But it is a tedious calculation, not very pleasant. So the theory was developed by a number of authors, and those people are just from our department, so I'm very familiar with this subject. Now, later approaches were, Schwinger was the first, I think, is just to use the mass operator of the electron, calculated in the external magnetic field. So this double line described the electron state and the propagator in external magnetic field, and this is a photon. Now, if you take the imaginary part of this diagram that is cut it that way, we will get the total by optical theorem, we will get the total probability of emission. So this is a more clever way. It is a more clever way to calculate radiation. It will be already summed up on final state of the electron. Now, calculations also in the literature, there were many variants of such calculations. I like most the original Schwinger approach using the proper time method. It is a kind of which reproduce the path integral in a way, but it reduces calculations to computing this sum over integral over internal momentum. You replace the integration that way. So first you make the parameterization, Feynman parameterization of the product of two propagators, and then you treat the exponential of ES by something as a Hamiltonian, this H as Hamiltonian acting on a fictitious particle, and you replace the integration over K as summing over the states of the, averaging over the states of this particle. So finally, it amounts to calculating this pi is the generalized, it is the generalized momentum, which will now be the function of proper time S. Is a fictitious proper time, of course, but it is, of course, related to true proper time if one uses instead the path integral. And you should calculate those pi as classical evolution of momentum in the magnetic field. And this can be done explicitly. So it gives you some integrals. So finally, you obtain the taking also everything on shell, you obtain this kind of expression in terms of double integral over U and S. Now, this is also similar to results of massive theory, And the difference is that the approximation of those integrals fail. So you have to look for another approximate ways, if we like to calculate the obtain result analytically, of course. So first, there is an oscillating factor here, oscillating factor psi. So using this, we can try to use something like stationary phase, but it is not true stationary phase because it is finally one that can construct asymptotic series. So the first terms of series in this series will be converging, and then some diverges. But it is enough to get a reasonable approximation. So the method works if the initial Landau number is big, and final Landau number is also effectively big. So you formally you sum up all of them, but it is effectively. So it is a kind of classical regime. And there is also a restriction from above on this number of Landau number, because finally calculating the mass operator and taking the imaginary part, we get the decay rate. So this will gives you imaginary part for the Landau levels. And the restriction comes from the fact that they should not intersect. So gamma should be less than the difference of two neighboring levels, difference of energy of two neighboring levels. This gives you another restriction. So, but still there is a window of validity. It should be less than 10 to the power 7, but much more than 1. So it is reasonable in some region of parameters. So this is so final result is just the simple integral, which have some divergences in both ends of the interval, but divergences are integrable. And finally, you get this formula. So this is the total probability of emission of a photon by the massless electron moving in magnetic field. What we see that it is non-analytic in terms of E, the electron charge, and this is because we use the background method and use propagator and magnetic field exact sense. To get a spectrum, in addition, we have to perform some Fourier decomposition inside this formula for mass operator. Just inserting here this quantity exponential for omega tau. We get finally some modified expression and extract the spectral power. Finally, repeating approximations and just the approximation consists in expanding everything in terms of x here and then integrating integrals, or lower power of x will be convergent and larger power will be divergent, but we understand that it is just a asymptotic series. So we consider it correct. Finally, this is the result for the spectral power of massless charge, of radiation from massless charge. There is a coefficient which just, this pi is a normalized spectral distribution, normalized to unity. And this is such expression where V is the ratio of H omega over the energy. So it is a fraction of the energy which was emitted in the single act of radiation. But it is quantum result, so it is just the probability. But in what we see that our calculations which were shown were taken for scalar particle, spin 0 particle, then this spectral distribution is just for the 0 particle. It is red here. another curve for spin 1/2. So the maximum of spectral power is at the 1/3 of the total energy. So that means that it is a hard radiation. Massless particles emit hard radiation. And this is the reason why there is no classical limit. Now, at the region of small frequencies, this behavior is just power law, and the power is just omega of 1/3. It reproduces the classical result and coincide, all coefficients, of course, coincide with it. So this confirms that classical theory describes radiation, well described radiation, but only this part of radiation. But the rest is just should be taken from quantum theory. So the average photon energy calculated by this distribution is 4/9 of the energy. The same for spin 1/2, with some difference that the normalized spectral distribution will be that way. It diverges at the limit. So V is the ratio of H omega over the energy. It diverges the upper limit when V is equal to 1. But the divergence is integrable, so there is no problem. And this is shown in the same picture by blue. Using both formulas, yes, and in low frequency region, the same as both coincide, spin 1 and spin 0 and spin 1/2 coincide with each other in this classical distribution. It is just the power 1/3. What is interesting that if you do the same for spin 1, you get divergence from the very beginning, and this shows that massless particle, vector massless particle charged probably should not exist because they could not interact with photons. This was, in fact, it was also discovered by Kayes and Gazyarovich some 50 years ago. From other considerations, of course, just looking for general formulation of spin 1 interaction of massless interaction, massless charge with massless radiation, with massless photon. So this is seen also in our radiation theory. Now, integrating over spectrum, we obtain now the correct result for the total power. Instead of diverging Larmor formula, which we should have there, this one. And the difference with another, which I obtained using just the cutoff, is just numerical coefficients of the order 1/2. So only numerical coefficient is different here. And the correct formula is there. Again, we observe that it diverges when Planck constant is sent to 0. So synchrotron radiation from massless charge, and this is general case of radiation from massless charge because I have shown from at the beginning that the accelerations are orthogonal to velocity, so kinematically it will be a rotation over a circle, and this is a general case. So it is essentially quantum. So this is my hard kick instead of soft hair. And it doesn't depend on the... another interesting property that both distributions, this is 1/2, spin 1/2, and this is spin 0. Both distributions do not depend on any parameters, only V, which is the ratio of H omega over energy. So spectra do not depend neither on magnetic field nor on the energy of a particle. Any massless charge which generated, or I don't know how it can arise in the magnetic field of the Earth, it should radiate along with this distribution, spectral distribution. Another question, what about trajectory? So once people knew that Larmor formula is diverging, they tried to calculate radiation in a local manner, like Dirac, considering the radiation reaction force. So taking not retarded potential, but the difference retarded and advanced potential was just used by Dirac to derive the Lorentz-Dirac equation. This was done by Kaczynski and other people from Tomsk, and they obtained the Lorentz-Dirac analog for massless charge. But the strange feature, well, first that the derivative was as high as fifths in the finite term, and there were some divergences more than mass. For Dirac, it was enough to renormalize the mass of the electron, supposing that the bare mass is infinite, and then it cancels the divergence of the proper electromagnetic mass. But here there are three different divergences, depending on different structure of derivatives, because the meaningful only from the fifth derivative. So the equation exists, but it looks somewhat strange. But now we understand that the equation has no meaning. One cannot use it because actually the trajectory will be stochastic, because in every act of radiation, the energy loss of the particle is of the order of the energy itself. It is 1/3 or 4 over 9 and so on. So another argument why massless particles do not move classically. So there is the final answer, and that electron does not move. We started from motion in external field, in the fixed field. But now interaction with electromagnetic field shows that it radiates quantum mechanically, so it radiates, it gives discrete acts of emission with hard kicks, and it is not motion along the trajectory at all. Another reason why it should be so is just so-called Betatron oscillations. In the theory of accelerators, it is well known that there are another quantum effect, which is just generation of Betatron oscillation due to radiation, and it is calculated. There is another quantum number than Landau number n, and this is just excitation of this second quantum number, which is Betatron oscillations. And it gives you another parameter of the energy, which is that way. So the H0 is the Schwinger magnetic field, which is equal to 10 to the power 13 for the electron. But now the mass which enters here in this parameter is such that it is strictly zero. So it turns out that the fluctuation threshold is just zero. So there is no region where motion could be classical for massless charge. So finally, two results. So first, probability of radiation is well described by quantum formula. It is a universal formula, not depending on field and the energy. And using this property of radiation, we obtain that motion will be stochastic, like Brownian motion. Now let's do the same for gravitons. First, we can calculate the emission of gravitons by the same charge. So I will not show all details. This is technically interesting because this is split into two parts. One part is proper gravitational radiation by the charge, like matter source. And another is just combination of external magnetic field and radiation, electromagnetic radiation tensor of the charge. This gives another stress tensor. So there are two stress tensors which generate radiation. One is called the Gertzenstein effect, which was the first to predict that the electromagnetic wave propagating an external magnetic field will transform into graviton because they have there is a resonance there, and that's just this part of gravitational radiation will be proportional to electromagnetic radiation, which we already discussed. So this part of gravitational radiation will have the same property. It cannot be described classically, only in the low frequency part. And quantum description gives you hard kicks in any act of radiation. Now the proper radiation, gravitational radiation, also gives you the spectral. It technically the same as electromagnetic, so it is another combination of Bessel functions. And finally, you get this formula, which gives you omega to the power -1/3. So it is decreasing, but not enough, because it's non-integrable at large omega. So you cannot integrate this. So it is still power divergent total energy. So gravitational radiation by electromagnetic source, which is the electromagnetic source is just the particle itself and its electromagnetic field. So you should take them together. Now what we do, we correct the spectrum at the quantum frequency, the total part. So we just cut the spectrum. What we obtain, so this just theta function cut off. We obtained that the average energy of graviton emitted, average energy of radiation emitted in one emission act is 2/pi energy. Again, such radiation will give you hard kick on the particle, so particle will not move along trajectory. And radiation is essentially quantum as well as in the electromagnetic case. Now, finally, it is a relativity, so-called gravitational synchrotron radiation. It's a purely gravitational effect when there are circular orbits for ultra-relativistic particles. They are close to null geodesics, which is 2/3 of gravitational radius, so it's Schwarzschild black hole. For Kerr, similar formula. And you can calculate the radiation spectrum using some approximation, of course, or using, if someone knows better how to deal with Hein functions, it would be better, but we use just approximations. And finally, if the radiating particle is still massive, so our formula obtained in 87 was that way. So there is mu is the mass part of the particle, gamma Lorentz factor, and this mu gamma is the energy. It remains finite in the limit of gamma infinity and zero mass. But there is a pure logarithm gamma which diverges. So finally, from this formula, it can be seen that radiation diverges in the massless limit. So radiation from the photon, calculated classically, photon is moving along the circular geodesic, will be infinite. So it's not big, it's not small, it is just infinite. So if particle is scattered and then one circle or several circles around black hole, classically it emits infinite radiation, and that's it. Now the reason is the same. If we calculate spectral power in terms of harmonic of the frequency of rotation, we find that now divergence is logarithmic. So it is going down, but not sufficiently. So finally you get that logarithm reproduced here. And that's all. So finally, what I want to say that massless particle can radiate. It could radiate if we had the massless charge in electrodynamics. But there are, in general relativity, there are such particles, photon or graviton itself, And classically, if you calculate radiation classically, it gives you infinite results. So what does it mean? It means at first that classical claim that massless particle, point-like particles, move along null geodesics is not correct. So what we measure when deflection of light ray in the field of a sun, we measure not only classical effect, but we understand that quantum corrections, if we know how to calculate them. So we should quantize gravity, we should calculate, and we obtain small corrections, of course. And so in average, it will move along geodesic, but in average. But strictly speaking, if you insist on classical calculation and you use the notion of point particle, but only for point particles in general relativity, we should have geodesic motion, as you know. For black holes too, but only in the asymptotic sense, so in some sense. Okay, so conclusions are, first, QED with external magnetic field consistently describes synchrotron radiation from massless charge. Of course, pair creation too. I calculated also pair creation of such charges by photon. It does not diverge, so the formula is okay. And so where to take this charge? We just, if it exists. So we just should consider creation by the photon in the magnetic field. So it will be already in bound state in external magnetic field. So there is no problem with no collinear divergences at all because absence of free particle states. Now radiation is stochastic. And classical theory still works, but it describes just the low frequency part of radiation. It contains no ultraviolet cutoff. The same is true for gravitational radiation, and so we have, in general relativity, we have a kind of ultraviolet catastrophe which demands the quantization. So it's another independent argument, can consider as another independent argument apart from the problem of singularities. Now, again, quantum nature of radiation, hard kicks, implies that particles, strictly speaking, do not move along null geodesics. And what we measure in deflection by the sun is just not only classical, but also quantum gravity, because we don't know which quantum gravity is correct. We can imagine that some quantum theory which would predict in other formulas for radiation. And in those other formulas, the radiation could be not small. But in our case, in perturbative Einstein quantum gravity, it is small, so everything is okay.